Now, all this talk of patterns and sequences and sigma notation leads us to this concept, the series, which is super important for calculus. It's one of the major components of a good calculus class. And a series is just a sequence that's been added together, I guess. You just replace the commas with plus signs. So here are the definitions of a series. First, we have the finite series, which is just the sum of the first n terms of a sequence, also known as the nth partial sum, which showed up in your last class activity. And it is, of course, denoted by a sub 1 plus a sub 2 plus dot 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 a sub n, and that can be written in sigma notation like this. Now, the second definition is for the infinite series, which is what you're going to deal with in calculus. The sum of all of the terms, all of them, of an infinite sequence is called an infinite series. And of course, it is denoted the same way, a sub 1 plus a sub 2 plus dot dot dot. But in this case, of course, the upper limit of the sigma notation has an infinity, showing you that that sequence goes on forever. This is supposed to be an I. Sorry about the bad writing there. Let's look at these finite series and some formulas that you need to know. So we're going to start with this theorem. It is for the sum of the first n terms of an arithmetic series. And sums, when not written in summation notation, are denoted with a capital S with a subscript n. So this is the sum of the first n terms of an arithmetic sequence, where a sub 1 is the first term and a sub n is the last term of that finite sequence. If you've ever taken a math counts class, then you probably learned this sum formula. It was proved and derived by Gauss. So what he did was he added the series to itself, but in reverse. So he took the original series, a sub 1 plus a sub 1 plus d. Because it's arithmetic, you have some common difference that you add. And the next term is going to have 2 times the common difference added. And you can do that forever. If you think about the sequence going backwards, you have a sub n at the very end, and right before that, you have a sub n minus d. So you're adding the common difference every time, but if you thought of it in reverse, you'd be subtracting the common difference from the last term. And so what Gauss did was he added the sequence to itself, but instead of adding a sub 1 here, what he did was he added a sub n. And then he added the next term before that, which was subtracting the common difference once. And then if you kept going, you'd subtract the common difference twice, plus dot dot dot. And then thinking about the sequence going the other way, you'd have a sub 1, and then a sub 1 plus d. So you take this sum, and you take that sum, you add them together, but you reverse the order. And then what do you get every single time? Well, this is a sub 1 plus a sub n, right? And then if you look at this sum, the d's cancel, so you have a sub 1 plus a sub n, and then another a sub 1 plus a sub n, because those common differences are going to cancel out, and you go all the way to the end where you have another a sub 1 plus a sub n. So you have pairs of the first and last term added together. There happen to be n of these pairs, and it equals to twice the sum. So if I rewrite this using multiplication, I have n times a sub 1 plus a sub n equals 2 of the sums. And so if I want to know what one of the sums is, then I just have to divide by 2. And this is where that formula comes from, very cleverly derived by Gauss. Now let's move on to the second theorem. This one is also a formula for the sum of a finite series, in this case the geometric variety, and therefore it has a common ratio of r, And in this case, the common ratio can't be 1 because then it's a totally boring series. And it's the sum, the partial sum is the first term times the quantity 1 minus r raised to the n, all divided by 1 minus r. And I'm going to derive this formula for you now in a very similar way as I derived the last one. I'm going to take s sub n, the sum, which in this case, since it's geometric, it has a multiplier. So it's a sub 1 plus a sub 1 times r plus a sub 1 r squared plus dot dot dot. And if I continued on with that series, I'm going to end up with a sub 1 times r, not n times, but n minus 1 times. And this one has a little bit of trick to it. So I'm going to now subtract off the ratio times the sum. So I'm going to take this series and multiply it by r and subtract it off. And so when I multiply this by r, it shifts the series. So a sub 1, the first term, becomes a sub 1 r plus a sub 1 r2 plus dot 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 plus, and then a sub 1 r to the n minus 1. And what that does is it adds on the term a sub 1 times r to the nth power, because I multiplied everything by r, and then when I subtract them, what I get over here is s sub n minus r times s sub n. And then when I subtract all these off, well, I get a sub 1 in the very beginning, and then these two cancel when I subtract, those cancel when I subtract, all the way down the line, those cancel when I subtract, and what I'm left with is minus, because I'm subtracting, a sub 1 r to the nth power. And then I can do a little bit of factoring, so I can factor out the sum here, and I get 1 minus r, and I factor out a sub 1 here, and I get 1 minus r to the nth power, and I want to know what the sum is, and so then I divide, and I have my sum formula. Now we're specifically going to look at geometric series, but in general, the two types of series that you have are the convergent type and the divergent type. Now, divergent, the example I'm giving you is 2 plus 4 plus 8 plus 16 plus blah, blah, blah. And a series is considered divergent if what you're adding each time makes your sum or your series blow up to infinity. So it just gets bigger and bigger and bigger and bigger and bigger. So a series is going to diverge if the sum becomes infinitely large as the number of terms becomes infinitely large. And you can never find the sum of that. It just blows up to be some huge number. Now, that's in contrast to the convergent series. And a convergent series has something being added on that gets smaller and smaller and smaller and smaller. So instead of blowing up, what you have is a sum that's going to approach something like an asymptote, and it's said to converge to a single value. And we can actually figure out what that value is going to be. And my first partial sum is 1/2. My second partial sum is 3/4. My third partial sum is 7/8. My fourth partial sum is 15/16. And so if I think about what happens in the numerator and denominator in relation to n, what the numerator is, it's a power of 2 that's had 1 subtracted from it, and the denominator is plain old 2 to the nth power. And that's the formula for this sum. Now, if I break it up, 2 to the n divided by 2 to the n minus 1 over 2 to the nth power, this 2 to the n over 2 to the n is 1, and I'm subtracting off 1 over 2 to the nth power. And this is the key to figuring out what this series is going to converge to. So if I think about it, what happens to this value, which is s sub n, as n approaches infinity, meaning becomes infinitely large? Well, this value here as n is infinitely large, converges to nothing. It becomes infinitely small, and so I'm subtracting off something infinitesimally small at the end from 1, so therefore this sequence here, 1/2 plus 1/4 plus 1/8 plus 1/16, is said to converge to the value of 1, because as you find more and more terms and you add more and more terms, your answer is getting closer and closer to 1. And you can see that just in these terms here, that this series is going to converge to 1. Now, these convergent series are the ones you're going to study in calculus. And if you're looking only at geometric series, knowing that these series have common ratios, you can tell by just the ratio which one's going to converge and which one's going to diverge. Because if you're multiplying by something greater than 1, your values in your series are getting bigger and bigger and bigger. And the only way to get what you're adding each time to decrease is if your common ratio is less than 1. So here's the rule for having a convergent geometric series. That common ratio, or the absolute value of it, I should say, should be less than 1. And this leads us to theorem 3, one about the sum of an infinite geometric series. And here is the sum formula. It says the sum is equal to a sub 1 divided by 1 minus r. I accidentally made a little dot there, so it looks like I, but it's really a sub 1. And you can figure out where this comes from just by looking at theorem 2. And if you look at the formula for theorem 2, and you just kind of think about what's going on when the absolute value of the ratio is less than 1, this thing here is some fraction that's less than 1. So as this n value approaches infinity, this value here basically becomes 0. So then what you have is 1 minus 0 over 1 minus r, which just means you have a sub 1 over 1 minus r. Now, one cool thing you can do with the series is to reimagine what a repeating decimal is. A repeating decimal is really an infinite geometric series. So for example, if I have 0.34 repeating, if I think about what this is in terms of a series, it's 0.34 plus 0.0034 plus 0.000034, and every single time I'm adding 2 0 decimal placeholders there, which means that this actually has a multiplier. In this case, the multiplier is 0.01. So therefore, my common ratio is 0.01. First term, which is 0.34, and then 1 minus that common ratio, which is 0.34 over 0.99, or 34 over 99. Now, you may have learned the trick about repeating decimals. The number of digits in the repeating block, you put that over the number of nines. So if that were 3.345 repeating, then you'd say 345 over 999. Well, that trick comes from the fact that you can actually review repeating decimals as series. So that trick you learned in math counts is actually from the sum of an infinite geometric series.